Okay.
All right. Thank you, everybody. This is Mike Parker. Mike Parker is an engineer with years of satellite communications experience, and he's going to give us a little talk about the link budget. This is for anybody in the Rebel Sat community who wants to learn more about what we're doing on the communications team. And really appreciate Mike taking his time to share with us. So Mike, please take it away.
Okay, well, see if this works.
Okay, I see it.
Do you see it? All I see is the update to Zoom. Let me slide this over here.
Yeah.
Do you see a screen now?
Yes, I do.
Okay. So is that okay? Shall we start from there?
That sounds good. Go to it.
Okay, so I'm here to talk about satellite to ground propagation, what is path loss, and what are some of the other propagation factors you need to consider. So the path loss is, to me, was always very confusing when people would say there's path loss, and then they would give me the equation. I say, where in the hell did that equation come from? So finally, I figured it out all by myself, and then this is my version of path loss. So if you start off, first of all, from you have an uplink and a downlink. The weakest part of your communication path on your command and communication radio is usually the downlink, because the satellite's always power limited. So can you see my mouse okay as I move it around? Okay, so up here in the upper left of this screen is where the transmitter is up in the satellite. And it's transmitting in this example, I'm going to use the example of 1 watt. And there's a thing called effective radiated power, which is the transmitted power times the gain of the antenna. And so and that's the EIRP, effective isotropic radiated power. So if I had 1 watt and I had a 100 dB gain antenna, the effective radiated power would be 100 decibels above a watt. But right now I'm going to assume this is an isotropic 1 watt radiator, which is sort of typical for a CubeSat. And there's a path down to the ground, has a range that we'll call R. And as it hits the ground station, there's a certain power density. And the power density, just from geometrical calculations, is the transmitted power divided by the area of the surface of this sphere that lies at the ground station. So 1 over 4 pi r squared. 4 pi r squared is the area of a sphere at a radius r. So the power density is the radiated power divided by that area. In this case, watts per square meter. And so as an example, if you have 1 watt transmitted, your typical range might be 2,000 kilometers out towards the horizon. And when you run the calculation, you get a power at the power density at the receiver of something close to 1.99 times 10 to the minus 14th watts per square meter. So that's pretty obvious stuff, I guess. You saw that in physics. Probably in high school, you had a candle here, and you calculated how much light the candle is casting on this area. So, saying a different way, the signal power out of the receiving antenna, which is going to be here on the ground, is equal to that power density times whatever the effective area of the antenna on the ground is. And so if you write the equation, the received signal is equal to the power density times the area effective. That's what's going to be the received signal. And you solve that, and you now know how much power is on the downlink. So this is effective area. What's the effective area of the antenna? Sometimes gets people confused. With a dish, it's pretty easy. Here's a dish looking into the dish, and this is like a bucket, and it's collecting the photons that are coming down to the ground. And its area, of course, is just the radius of the dish squared times pi. And Similarly, with if you had a rectangular antenna, it would be the area of the antenna height times the width, simply. And so you'd have that area is the area of the antenna. And then there's a fudge factor, which is the efficiency of the antenna, which for a dish might typically be between 50 and 80%. So if you have that area effective number and you went back to that previous equation, that times the intensity would tell you how much power is going to come out of the antenna connector on the receiver. Simple, huh? So,
is the antenna efficiency like for Yagis? What's it average?
Well, we're about to get there. Thank you. Good, excellent question. So over here, down here, you see this antenna. So here's the dipole, and in this example, I made a collinear array instead of dipole, and a dipole beside it, and a dipole down here, and dipole down here. It turns out that the effective area of the dipole includes sort of the area of the subtended by this entire array, including the vacant area in the middle where there is no dipole. Because the resonant dipole has a certain capture area that's something like a half a wavelength or so all around the dipole. So for a Yagi, and here's an example over here in the picture on the right, are two Yagis. Look at the long one. This one has in it 40 elements, 20 vertical and 20 horizontal. And that's an 18 decibel, it's Yagi with 18 decibels gain, and we'll talk about decibels in a minute. But it's almost a factor of 100 times the incident power. So you can have, let's see, I think I picked this. And so there's an equation that's pretty useful to know about, which doesn't involve the size of the antenna, the dipoles directly. It's the effective area of antenna is the gain times the lambda squared over 4 pi. And so lambda is the wavelength of the signal. In the case of 436 megahertz, it's about 70 centimeters. So if you are 0.7 meters, so you take the wavelength and you square it divided by 4 pi, and that's the effective area of a 0 dB gain antenna. So then you have to multiply that by the gain of the antenna, which I think I told you was slightly almost 100, and that will end up with the effective area. So here's if you know the gain of the antenna, you can, now we're back to that first equation we looked at. The signal power of the antenna is the power intensity times the effective area. If you know those two things, you're almost done. And so this is on the first slide was the effective radiated power divided by the area of that big round ball that was being illuminated by the antenna.
So when you say effective area on that equation, is the effective area would be, if you weren't going with just the real area and the efficiency, if we had a Yagi, for instance, the effective area would be that eta and the A. It would be that whole term.
Be the effective area of a Yagi, or any antenna where somebody just says the gain of this antenna is such and such. The isotropic gain is multiply that times lambda squared divided by 4 pi, and that'll give you the effective area.
Okay.
So if you plug all those numbers in and you work them through and cancel terms, you end up with this equation right down here. That says the signal received power is equal to the transmitted power times the gain of the transmitter times the gain of the receiver times lambda over 4 pi r, and the whole thing squared. And here's where things always got confusing for me until I finally figured this out. Say, what in the world people were calling this term, lambda squared over 4 pi, the free space path loss. And I quote right out of the official Wikipedia statement. That's misleading because it's not, because how can path loss have anything to do with the wavelength? All it can have to do with is the spreading of the energy that gives you the intensity of the antenna times the area of the antenna. There's no wavelength terms in that first equation. Where the wavelength comes from is not the path loss. Truly, it's the gain of the antenna.
And that's a dimensionless quantity because you got wavelength on the top and radius on the bottom.
The gain of the antenna changes with wavelength, and that's and the gain of the antenna changes with and all that's equivalent to saying is the effective area changes with wavelength. So if you have a great big dish, it's receiving. Well, I'll give you an example out of my head. We're using a 6-meter dish that has and it runs at a wavelength of 3 centimeters. And so you plug in, you change the parameters around to solve for gain, and it turns out that's about 50 decibels. That's a really big number, 10 to the fifth. Mm-hmm. If that wavelength was 70 centimeters, which is the frequency that we're going to use for command and control at 436 megahertz, that gain would be on the order of 25 decibels, or something on the order of 300 and 3 times 10 squared rather than 10 to the fifth. So what happens is if there are many wavelengths across the aperture of the antenna, then that means that the beam of the antenna is really long, really strong and narrow. All that energy that was going to be received from all around you all gets bunched up and phased up and added in the direction of the main beam. Does that make some sense to you at all?
Yeah.
So you have two choices. If you insist on taking this nice little slider rule that I'm going to send to you, hopefully you can still see this. Maybe not. But anyway, if you take that and you use it literally to calculate free space path loss, you'll end up solving with this equation, or this is called the free space path loss. But if you want to remember the physics of the problem, you'll do it the way I just told you. Calculate the intensity hitting the antenna, which is proportional only to the range squared, 1 over that, and the effective area of the antenna, which is this equation here. And just take that and multiply those two. So that's what I remember. And once I remember those two things, I can solve just about any problem involving how much power are you getting out of the antenna. Now, I came prepared because I know that a fair number of the students, especially out of let's see if I can get this to change here. There we go. Especially out of the computer science department, don't know what a decibel is. So everybody raise their hand if they know what a decimal is, or maybe it isn't. And I'm not going to go through all this equation-wise, other than to say that decibel is a way of representing things that makes things convenient. It's the ratio of powers. So if you have a power ratio that's a factor of 100, if you take the logarithm of that, that's multiplied by 10, that's 20 decibels. One of my professors once told me that if you have a teenage boy the amount that the music gets turned down when you say turn that radio down is 1 decibel. It's a relatively small number. 3 decibels is a factor of 2 in power. 6 decibels, double that is a factor of 4. 10 decibels, and so you see this is all a logarithmic scale, and it also has negative terms in it. So if the power coming out is a tenth of what went in of any circuit, it's minus 10 dB. So when people are telling you the gain of this antenna is 10 decibels, what they're really saying is the power ratio is 10. If they're telling you the gain of the antenna is 20 decibels, they're telling you that it's a factor of 100. Why do we care? It's because it's convenient to add numbers easier for most people to add numbers rather than multiply them. And so if I have an equation like we were looking at before that had a lot of different multiplies and divides, if you turn everything into decibels, it'll turn out that all you have to do is add and subtract and make your life a lot simpler. So if I start off with this effective radiated power, that's the power of the transmitter times the gain of the transmitter, gain of the antenna. And we said 1 watt for a CubeSat is pretty typical, which could be also just somebody might also talk to and say it's 1,000 milliwatts. So a milliwatt is 1,000th of a watt. So that makes a lot of sense, doesn't it? So if you express this in decibels and you said in decibels above a watt, this would be 1, but we're going to express it in milliwatts for you'll see why later. So 1,000 milliwatts is 30 dBm, decibels above 1 milliwatt. And this was a spreading loss that we calculated earlier, out to 2,000 kilometers. And that was it. And that was turned into decibels is minus 137 dB per square meter. So we take these two and add them together, you end up with 107 dBm, decibels above a milliwatt per square meter, which is a pretty weak signal. But that's what satellite signals are like. And then we had if we had an isotropic receiver, it receives equally in all directions. This is the magic formula, lambda squared over 4 pi, wavelength squared over divided by 4 pi, would give you point at 70 centimeters or 0.7 meters. You work that equation, it gives you 0.039 square meters. And you turn that into decibels, it's minus 14 dB square meter, which is 14 decibels below a square meter. And then we had the gain of that Yagi, which was 18, which would be 18 decibels power ratio of what comes in to what comes out. So we take all this number and these two numbers, add them all up. This is what's actually coming out of the antenna, and that's now we've solved the path loss equation for signal power coming out of the antenna, which is half of what you're interested in. Because what you really want to know is what is the signal to noise ratio? What is the signal power divided by the noise power? And if you have signal to noise ratios that are maybe a factor of 10 or better, it's pretty easy to receive that signal and receive it with it pretty accurately with a small number of bit errors if you want to turn it into bits. If the signal to noise ratio gets below 0, it's pretty hard to get anything other than random noise coming out of your receiver. So we have signal power here, and now we're going to go find the noise power. But before I do that, I should stop and ask if there are any questions.
No, I'm with you.
Okay. So let's talk about noise. And if you're really interested in noise, there's a good reference here in the EITU, which stands for the International Telecommunications Union, which is the international organization that tries to tell people what would be a good way to calculate things. for radio communications. And so noise sources are oftentimes expressed in terms of the temperature of the source. So if I say the Earth is, well, let me back up. The Earth is on average about 290 degrees Kelvin. Well, there's, from physics, if you go look in physics textbooks, you'll see that as the Earth's temperature increases, the amount of noise at any frequency increases linearly with temperature. And all this is an approximation that works until you get to a really high frequency, almost into the infrared. And that's in this case, maybe 300 gigahertz, 300,000 megahertz. So a lot higher than what frequencies we're going to be interested in with our radios. So and I didn't write it down here, but the noise temperature times the Boltzmann's constant. I'm sure everybody knows what Boltzmann constant is. Right. That was a joke. But it's just, here it is right down here. Boltzmann's constant is 1.38 times 10 to the minus 23 watts per degree Kelvin per hertz. So what this says is that if I have something that's 1 degree Kelvin, which is pretty darn cold, and the noise is within a 1 hertz bandwidth of a receiver, is 1.38 times 10 to the minus 23rd watts. So if you start plugging in some real numbers, this of course gets bigger. A real number might be, well, in fact, I worked it out up here. And let's walk through this. I have noise that comes from the sky. That's going to be from various sources like radio sources, synchrotron radiation from the electrons orbiting the magnetic field of the middle of the galaxy. Things of that nature. You can go look in this thing and you'll find that reference, and you'll find the sky pictured as over at this particular frequency, and that runs typically between 30 and 40 degrees Kelvin, which says the sky is not as much radiation is coming from the sky as coming from the Earth, but there's still at this frequency still a fair amount, and most of it's coming from the Milky Way, and a bit from the sun if the sun's active, and then other small sources. But in addition to the sky, you also get thermal noise from the Earth, and why that is of course it's because your antenna, if you're sometimes it's pointing at the Earth, at least its side lobes are pointing at the Earth. So if you take a typical antenna and a typical pointing, you might get, it is a function of how the antenna is designed and all kinds of stuff, but you might get 50 degrees Kelvin coming from the Earth, forcing its way into the antenna. So the sum of these two temperatures is 30 to 50 plus 50 would be between 80 and 100. And this is very just gross approximation. But wait, there's more here. So first thing that's going to happen coming out of your antenna, you probably have a coax cable that's going to route the signal to an low noise amplifier. And the thermal noise in the coax cable itself contributes some to this temperature. And I'm going to refer you to textbooks on this as to how this works in the equations. But if you take that slide rule I'm sending you, you'll be able to look it up straight on the slide rule. So the more loss that you have in the coax cable, the more noise that the less noise coming from this Earth and the sky because you have attenuation, but the more noise that's coming out of the cable itself. So if the cable itself is the typical Earth temperature is say 290 degrees Kelvin, and you have a 1 dB loss, then there's 60 degrees degrees Kelvin of noise coming from that cable. If the cable were really attenuated, like maybe 10 dB attenuation, you would have the noise temperature would be what? It would be same as the temperature of the cable, which would be 290 degrees Kelvin.
So should that be an equal sign, not a plus sign there?
No, I'm just saying the 60 is a 1 dB loss, and what I'm trying to say is add 60 degrees Kelvin to the sum of these two numbers.
Right, but 60 degrees is equivalent to
1
dB,
1 dB
loss.
At
So that should be an equal sign.
degrees Kelvin. Now, so if you wanted to, if you had a coax cable and you wanted to decrease the loss, one way to do it is to make just toss it in dry ice or something, make it really cold. Now the temperature of your cable might be 100 degrees Kelvin, and 1 dB of loss in the cable would be a lot less than 60 degrees Kelvin because the temperature, this number is not only, let's put it a different way. Let's suppose the loss for 10 decibels, almost all the signal is lost, and the only thing you see coming out of the cable is thermal noise of the cable. If you make that cable cold, T gets to be a small number down here, and the noise in that coming out of that cable is small. So what's the moral of this? The moral is you don't want to have a lossy coax cable between your antenna and your low noise amplifier. So one way to avoid that is to take your low noise amplifier and mount it right on the back of the antenna. So if you see back here, I don't think you can see it on this, but at the back of this antenna, the low noise amplifier is sitting right there, at least on my antennas. And so that it gets you back to a low loss, which means that the coax cable is not going to be a significant factor. If you on the other hand, we're say between my operating position and my antenna, maybe it's typically 100 feet, or 150 feet, 200 feet, and let me go get some typical cable, RJ58, nice 50 ohm cable, but it's small and it's flexible. It may well have 15 or 20 dB loss. The signal gets attenuated and the cable adds noise, and you don't hear much of anything. So if you do have to have a long cable run before your low noise amplifier, make it a really expensive cable that has a lot of low loss at these frequencies. And loss increases in these coax cables as you go up in frequency. So what may be a very good cable at 30 megahertz may be a disaster here at 436 megahertz. And then the next thing that happens is you go into a low noise amplifier that you would typically buy. You can build them, but it's hardly worth it. I can go to Down East Microwave, and for $85, I can buy one assembled that has a 35 degrees Kelvin noise figure. So that 35 degrees will get added to the coax loss in front, the thermal noise from the earth and from the astronomical sources. But this is a pretty decent number for an uncooled communications low noise amplifier. And of course, they aren't going to, very few, except for satellite systems, very few of these amplifiers are actually specified in degrees Kelvin. They're specified in a thing called noise figure. And 0.5 dB noise figure is the ratio of 35 degrees Kelvin to 290 degrees Kelvin. So the noise figure is just the ratio of what the noise temperature is divided by a standard 290 degrees Kelvin Earth. Don't expect you to remember that, but you'll end up looking up that formula if you don't. So if I did all this stuff and neglected radio frequency interference from other sources like fluorescent lights and switching power supplies are horrible animals, the little wall alerts that you get with your computers and stuff. And you computer some stuff, you get ignore all that stuff. Out in a nice quiet environment, we had 50 degrees from here, another 50 degrees from here, 32 degrees from the antenna, and 35 degrees from the low noise amplifier. Excuse me, 32 degrees from the coax and 35 degrees from the low noise amplifier. Add all that up together, my system noise temperature is 167 degrees Kelvin. I'm letting radio frequency interference. I'm saying, let's use this equation, KTB, Boltzmann constant times temperature times bandwidth. So if I have a receiver with a typically might be receiving with a 10 kilohertz bandwidth, that would be a typical receiver receiving CubeSat downlink at 436 megahertz. You multiply that out and you'll end up with minus, or if you don't like, if you would rather, you could add it all up, add these three numbers instead of multiply it in dB, and you get minus 166.4 decibels relative to watt within a 10 kilohertz bandwidth. If I wanted to have a 10 megahertz bandwidth, the ratio of 10 kilohertz to 10 megahertz is a factor of 10 to the third. And I would have 30 decibels more noise because the bandwidth would be a factor of 1,000 higher. And then, of course, quite often people like to speak in dBm, decibels relative to a milliwatt. So to convert from watts to milliwatts, that's a factor of 1,000. And it's fewer dB below a milliwatt than it is a watt. So that's the same, exactly the same power expressed in milliwatts. And so if I want to take the signal to noise ratio, then it's the number that I had calculated previously, minus 103. I add that to my, we got to go back and check. That was in milliwatts, so minus 103 milliwatts added to minus 136.4 decibels relative to a milliwatt. And so what is that? That's, if I could subtract that out, it would be about 33 dBm, which is a pretty decent signal to noise ratio.
Wait, you said minus and minus, or are you adding them, or are you subtracting them?
There are two minuses that I'm adding.
Okay.
If you want to, because we didn't say, because we use the negative sign to indicate it's below a milliwatt rather than 136 dB above a milliwatt.
So you're subtracting the noise from the antenna power.
Back in the equation, I'm dividing the, if you go back to this equation here, and I get, I'm sorry, that's the wrong equation. I don't actually have the equation written down, but yes, it's signal on the numerator and noise on the denominator, signal to noise. So I have a negative signal and I have a negative noise, and I subtract, because it's in the denominator, I subtract the negative noise, which turns this back into a positive 136.4 that I add to the signal number. So you're right, I was describing that incorrectly, I think. Are we okay now?
Yeah.
Okay, and finally, other effects that I'm just going to toss in for free. So here's your satellite. I think your satellite, your CubeSat was going to orbit at 400 kilometers.
Correct.
This is one of my favorite charts. It has nothing to do with satellites. It was designed by a Stanford professor to analyze the ionosphere, but I use it for satellites. This is all to scale. So here I am with a satellite, and I look out towards the horizon in a straight line, forgetting about any bending in the ionosphere. There's the going through the satellite. I go up here and I read this scale. And so at this point, at a range of about 1,800 kilometers, 1,850 kilometers from my receiving station is where the satellite is. My elevation angle is 3.5 degrees. Now the satellite's flying along here, rising, and it's in a circular orbit. I'm going to say it stays at 400 kilometers. When I get over to here, about half that original range, I'm now at 20 degrees takeoff angle to the satellite, as read from this scale here.
Right.
And so I just took a look at this and I said, well, when the satellite breaks the horizon, it's going to be somewhere out around in here, right close to I'm not really going to see the signal at this frequency if it's below the horizon. So it's going to be somewhere around here. And if I take bring that down to a curved Earth, it's about 1,900 kilometers. As a straight line, it's going to be about 2,000 kilometers.
So these distance figures take into account the fact that the Earth's curving.
Right. So they if you want to be exact, they do.
Okay.
And so when I say 2,000 kilometers, I just think, well, that's a reasonable approximation. I don't know exactly where it's going to break the horizons. Some days I might hear it at 0 degrees elevation. Other days I might not hear it until it gets up to, 5 or 10 degrees elevation, because there might be a tree or a mountain in the way on the horizon. So somewhere in the neighborhood of 2,000 kilometers, I just chosen that as an example. As the satellite gets over to this distance, you can see we're going to be about between 900 and 1,000 kilometers in a straight line away from the ground station. So this is just a convenient aid to, and if it were to go straight overhead, it would be 400 kilometers away. Because of course that's not only the altitude of the satellite, that's what the chart's telling me. Now, one thing you want to remember when you're doing this is the probability of the satellite going straight overhead is like near zero. The probability of it being somewhere in this range here is below, well, in this case, below between 20 degrees and over zero is about it's really higher than the probability of it being higher than 20 degrees. So especially for these low orbit passes, you got to run a bunch of your own orbits and see for yourself. But you're going to find that most of your passes will end up being at relatively low elevation out in this range, out in here. Very few will be near overhead. So this is why I like to choose one of the longer ranges as my target. I noticed that in your proposal, I think you used 20 degrees as your target range for one of your calculations, and that's somewhat improbable. That's probably going to be statistically one of your lower elevations in your pass rather than a typical elevation. And so when we're dealing with astronomy people, that's one of the first things I find is that they don't want to look at anything unless it's above 20 degrees, because the fluctuations for them in the atmosphere gets worse and worse as the elevation goes down. So they just go find if they have stars down on the horizon, that you go find another star up and lie something that's up overhead. But it doesn't work that way for satellites. I think that was other factors, yeah. So one of the things that happens, they should just be aware of, and I said transmit antenna pattern, I should have said received antenna pattern in the example I'm talking about here. That's my mistake. The signal comes in from the satellite at some elevation, and hits your receive antenna. What also happens is the signal comes in from the satellite, hits the ground, and bounces up into your receive antenna. And the effect of this is that right on if this is a perfectly smooth earth, the ground acts just like a mirror. So it acts just like, you can't really tell the difference between that path and the image, what they call an image antenna down here. So that you can calculate the difference in these two paths as being this line segment where the red arrow is pointing. And if that line segment is 0, it turns out this reflection flips the phase. So right at the horizon, there's a null if this is an ideal sort of two omnidirectional antennas with a flat Earth. There'll be a null right on the horizon, and then there would be a peak. It actually gets enhanced because when the phase changes by 180 degrees, the summation of two sine waves goes from canceling to adding. And then as you continue to raise the elevation, when this distance here becomes exactly a wavelength, what happens?
Cancels.
The sum of the two does what?
It interferes.
It interferes and you get a null. So here's an example for the 70 centimeter band that you'll be using for receiving. If the elevation of your antenna, you said, hey, I got a real smooth earth, I'm just going to put it up on a little pole, and I'm going to make that pole 5 wavelengths high, which is about 3.5 meters. Well, what's going to happen is, that's fine, you aren't going to have any, and there's no trees around, and this is smooth, no mountains, everything's cool. Well, what's going to happen is you're going to have a null, in this case, where there's exactly 1 wavelength difference in this path length here between. And that calculates out to 5.7 degrees. So if you were trying to receive a satellite, and then there'll be the second null, and it'll be 11.5 degrees, and etc. So what'll happen is you'll get an enhancement in between this where they sum together. So if you take two voltages and sum them together, the voltages are a factor of 2 stronger. But what that means is the power is voltage squared by Ohm's law. So you get a 6 dB enhancement at the peak right there. And then it'll be this really, really, really deep null. And then another 6 dB enhancement, and another really deep null. So what'll happen is the satellite comes along, you work your length equations and think, oh, I have 5 dB margin. And then you actually look at the actual traces, and you'll see the signal bumped up significantly higher than the margin. And then it dove down to way below, maybe a 20 decibels deep null sometimes. So it's just a thing that happens, and you have to be prepared for times when, no matter what your length calculations say, there's going to be signal dropouts.
But how quickly do these come? Because we got to send a bunch of packets of data.
So now we aren't talking length calculations, we're talking communications protocols. So it all depends on how you send the packets of data. If you say, I'm going to send a packet of data, but I can afford to miss 1 out of every 10, and I don't want it, and if I miss it, I'm just going to throw it away. But you might do on a downlink that's just transmitting telemetry, or maybe it's transmitting video.
It's not transmitting video, but it's transmitting telemetry data.
So you might say, well, if I have a null, I'll lose 10% of my data. Do I want it so bad that I want to retransmit that data? Or am I willing to say, I'd rather have the current data and not bother with the retransmission? Quite often, for telemetry data, it's okay to say, I'll just here's some good data. I have 9 seconds of good data. Here's a second of data loss. Here's another 9 seconds of good data.
No, we're doing experimental work, so we need the data. We can't just say.
It depends on what type of experiment you're doing. For example, if I were doing an experiment, which I am, on the CatSat, transmitting HF signals, if I'm listening to a HF voice signal or an HF data signal, and this signal fades, I just lose it for a few seconds.
Yeah, we're not doing that. We're doing a system where we're measuring a antenna thruster, and so we got to see the whole profile of exactly how the thrust and stuff changes over time. So
Right.
we can't lose a chunk of that. Or
So
that.
you're probably going to want to store your data, and then just this is more like TCP/IP. Although that's not necessarily the protocol you would use, but where it's not. Well, we used to instead of just transmitting packets of data and hoping for the best, which we used to call ship and pray, by the way. We want to have a valid errorless or almost errorless signal, which is what you want to have. So you might want to store it, and then when you transmit it, if the ground didn't receive it, it's going to transmit. Well, every time it receives a packet, one simple way of doing this, every time the ground receives a valid packet, which it can check and be fairly certain is valid by doing a cyclic redundancy check or some type of error control check on the data. What the ground then does is it says guide it and tells you what packet number it got. And if the ground didn't receive a packet, it does not send an acknowledgement. And in that case, the satellite says, wait a minute, where's my acknowledgement? And it knows that one of two things happened. Either the ground never received it, which means that the satellite has to retransmit it, or perhaps the acknowledgement half of the upload got lost, but still it retransmits the packet. It doesn't lose anything. So that's a very common ham radio protocol that AX.25 TNCs quite often use. This is a connected protocol where it knows it's a connection with the other side of the link, and so you'll hear two different signals going. One is a packet going down, and then it's answered acknowledgement going back up, and and then as soon as it misses one, you'll hear it try again, and it sort of gets out of sequence. So that's one way to solve.
About how long do we have where we're likely to have a decent communication window?
It depends on your height of your orbit.
450. I told you, 450 kilometers.
Am I answering the question you're asking, or am I answering a different question?
No, I'm asking how long. So we went all to the signal to noise ratio and the antennas and the noise. So basically, what does that mean in terms of how many minutes of overhead do we have to get where we're likely to get? Obviously, that changes with our antenna, but what's a reasonable, at least ballpark figure at 450 kilometers altitude? To how long can we expect for one pass? How long do we have?
I'm just sort of weighing this, but I'm thinking in the neighborhood of 10 minutes.
10 minutes, okay.
And you'll get, depending on the orbit, is this a sun synchronous orbit or a lower inclination?
I'm not sure.
Well, if it's going over the poles, you get a slightly different answer than if the orbits were doing. You launched out of Cape Canaveral and maybe had 30 degrees inclination.
I'll figure that out, but you say it's only a slight difference.
Well, so what you're going to get something in the maxing out around 15 minutes, maybe 10 minutes for a 450 kilometer orbit. But any of your programs that calculate orbits and there's plenty of them, and look angles, well, you just run a bunch of them and you'll know. But it makes a difference. The other thing that height makes a difference is how many orbits a day do you see. If you're in a polar orbit at 400 kilometers, you probably only see. Well, let's just talk about an example. It's reasonable to expect that you'll get reliable communications if you don't have buildings or trees or mountains in the way, from somewhere between 5 and 10 degrees elevation angle. up. And because things as you get lower get, in this case, obscured by the horizon, or in other cases, we get obscured by a mountain or a building or something. So it's strictly a geometry effect of for a pass. How long do you have a pass that's above? And let's just pick a number, 6 degrees. So this comes over the horizon. As soon as they hit 6 degrees, you get a pretty good signal with occasional fades, but pretty decent signal until it drops, until it goes over beyond the horizon on the other direction. And that time is dramatically affected by the height. So there's two things that happen. One is, as for higher satellites, it's going to be above the horizon for longer, and also you're going to get more passes. At this altitude, you probably will be lucky to get 2 north-going passes and 2 south-going passes a day. If you were orbiting at, say, 1,000 kilometers, you would get typically 3 north-going passes and 3 south-going passes a day. So plus the passes would be longer on each pass. So you just have to work the orbits out in equations and figure it out.
Okay.
Does that answer your question?
A bit. A lot of the questions, a lot of the specifics I got to figure, like you said, I got to figure out about what exactly our orbit is.
So at these frequencies, you don't get any significant bending. You don't get usually any horrible attenuation. So it's just a geometrical line, pretty much a geometrical line of sight. And if you're lucky, you don't get any radio frequency interference. If you're unlucky and you're in the middle of town next to an arc welding shop, you're maybe in deep bucky.
Okay. All right. All right. That sounds pretty good. It's an hour, so I guess we gave us more time than they said they would, or they maybe only cared about recording time. But that's pretty good. Yeah, I think that's a good, reasonably digestible chunk for our group. So
yeah, I really am sorry about putting equations up. Normally in briefings, I